The topic of the video is Heisenberg's picture. For understanding this topic better, I recommend you to watch my first video on Schrodinger's picture. In this picture, in Heisenberg's picture, the operators are assumed to change with time, and the state vectors of a system are assumed to remain unchanged with time. And it's actually the exactly reverse way of considering these in Schrodinger's picture. In Schrodinger's picture, a constant initial ket vector, uh, ket psi 0, was actually transforming to a ket at any time psi t with the help of an operator called evolution operator, which we called u hat, and its expression was uh, the exponential minus I h hat t over h cut, where this h hat, capital H hat, was uh, Hamiltonian of the system. If we reverse this equation for psi t, then we can get the equation for ket psi 0 as as a u dagger operating on ut, and if you call this psi at 0 as psi in Heisenberg picture, then psi h is equals to u dagger into ket psi t, and we can call this as equation number 1. And since it is just the initial ket psi of the system, it will remain constant throughout. That means your state function is not changing with time. Since this u is a unitary operator, and then the action of u dagger is happening on state vectors like psi t's, we can consider the equation number 1 as unitary transformation. And under such kind of unitary transformation for change of basis, then new operators in the transformed space will become u dagger into the operator in old basis and then u. And if you want to know how we are getting this expression, I recommend you to actually watch my video on unitary transformations. So the operator in Heisenberg's picture can be denoted as a sub capital H, and it can be written as u dagger a in Schrodinger's picture into u. And if you substitute u dagger from instead of u dagger, if you write exponential iht over h cut into a, and then instead of u, if you take u as it is, then we can get this expression number 2. And in this equation number 2, if you had instead of a, if you had dou a by dou t, then we can write that also dou a by dou t, but in Heisenberg's picture, and we can call this as equation number 3. And in equation number 2, instead of a, if you had a commutator of h into a, then here on the right hand side also we should have been writing the commutator of h and a, but in Heisenberg's picture, and we call this as equation number 4. And in the following, we try to actually derive an expression for evolution of operators in Heisenberg's picture. For that purpose, we take differentiation of with respect to time, and that's from equation number 2. So we'll do the derivative for the first exponential and keep a into the second exponential as it is, and we get this first term. And then when we did the differentiation just for a, we'll get dou a by dou t, and then we have these exponentials as they are, and then we keep the first exponential and then a as it is, and if you do the differentiation to this second exponential, we'll get this factor here. And we can write this first term and then the last term together like this here, and we can write the second term from equation number 3 as dou A by dou T in Heisenberg's picture. And these two terms can be actually written as this I mean in the bracket we get HA minus AH, and this we can write as a commutator of HA. And from equation number 4 we see that this term can be even written as HA in Heisenberg's picture. This equation that we had here for dAh by dt is called the equation for evolution of an operator in Heisenberg's picture. That's it in this video. Thanks for watching.